Microporous crystalline materials such as zeolites and metal organic frameworks have potential applications for use as thin layers in membrane separations. Such microporous membrane materials have a potential for separating a wide variety of mixtures. To give just 5 examples of microporous membrane materials, let us look at DDR, that consists of cages of 278 cubic angstrom separated by 8-ring windows whose aperture is about 3.65 angstrom. ZIF 8 has cages of 1,168 cubic angstrom, and each cage is separated from adjacent cages by flexible 3.3 angstrom size windows. This dimension 3.3 is from the crystallographic information, and we will see later that in practice there is a high degree of flexibility, and guest molecules significantly larger than 3.3 can cross the window regions. Another type of microporous material is X zeolite, Y zeolite. Both have the faugesite or FAU topology. It consists of cages of 786 angstrom separated by 12 ring windows whose aperture is 7.2 angstrom. We could have one-dimensional hexagonal channels of MOF 74, where M could be magnesium, iron, cobalt, nickel, manganese. Or we could have a set of intersecting channels and use MFI zeolite. MFI stands for mobile 5, and the channel dimensions is 5.5 angstrom, and this is a straight channel and it intersects the zigzag channel. These are the intersection sites. There are 4 intersection sites per unit cell of MFI zeolite. A wide variety of channel dimensions, window dimensions, cage dimensions are possible. And in this presentation, we focus on the important characteristics that determine the performance of a membrane, and that is the membrane permeance and the membrane selectivity. Ideally, we would like to have a combination of high permeance concomitant with high selectivity. However, normally the higher the selectivity, the lower the permeance, and there is usually a trade-off, and we will examine the various factors that determine the permeance and the factors that determine the selectivity of a membrane. One of the important things we would like to stress is that membranes in this category, consisting of narrow windows, have completely different characteristics than membranes that are constructed from materials that have larger channel dimensions or larger window dimensions. Let's see how a microporous membrane is constructed. Take the example of a ZIF-8. It consists of cages of 13 angstrom in diameter, and each cage is separated from adjacent cages by narrow 3.3 angstrom windows. These windows are flexible, and this flexibility allows molecules that are slightly larger than 3.3 angstrom to pass through these windows. Typically, the membrane would be constructed of thin layers of about 50 microns on a support, which is a macroporous. In this case, say a titanium support. And ZIF-8 is a good choice for separation of mixtures of, say, carbon dioxide, methane, carbon dioxide, hydrogen, methane, hydrogen. And the important advantage of ZIF-8 for CO2 methane separation is both adsorption and diffusion complement each other, leading to high permeation selectivities in favor of carbon dioxide. Let us examine the flexibility of the windows of ZIF-8. I'd like to show you animations of the window flexibility obtained by molecular dynamic simulations. What you're going to look at is a view that is along this direction. So let's start with the windows. We see that the window here is flexible, and it opens and shuts like a saloon door in the Quentin Tarantino movie, The Hateful Eight. This window flexibility is useful in that it allows molecules larger than 3.3 angstrom to cross the windows. In order to define the metrics that describe the separation performance of microporous membrane constructs, we examine a schematic for separation of a binary mixture of components 1 and 2. The membrane separation device operates under steady state conditions. The partial pressures in the upstream compartment are P1 and P2, and the partial pressures in the downstream compartment are P1 delta and P2 delta. The thickness of the microporous membrane layer is delta. The upstream face of the membrane can be considered to be in thermodynamic equilibrium with the partial pressures in the upstream compartment. The component loadings Q1 delta and Q2 delta at the downstream face of the membrane are considered to be in equilibrium with the partial pressures P1 delta and P2 delta in the downstream compartment. Commonly, P1 delta and P2 delta are significantly smaller than P1 and P2 in the upstream compartment, and therefore the component loadings at the downstream face of the membrane are significantly smaller than the component loadings Q1 and Q2 at the upstream face of the membrane. N1 and N2 are the fluxes of component 2 that permeate across the membrane. The permeability of the membrane is defined in the following manner. It is the flux of component I, n sub I, divided by delta P, which is the difference in the partial pressure of that component between the upstream and downstream compartment. So it is P1 minus P1 delta, P2 minus P2 delta. So the component permeability is Ni divided by delta P divided by delta. And let's call that P or pi. If we write a simplified expression for the flux, we obtain the following expression for the component flux. It is rho, which is the crystal framework density of the microporous material, the Maxwell-Stefan diffusivity of component I times the difference in the component loadings between the upstream and downstream faces of the membrane, delta Q, divided by delta. And this expression simplifies to rho times the Maxwell-Stefan diffusivity times the ratio of the component loadings at the upstream face divided by the partial pressures in the upstream compartment. And in this expression is valid in the special case in which the downstream partial pressures are negligibly small, and so are the downstream component loadings Q1 delta and Q2 delta. The component loadings are accessible from molecular dynamics simulations of the Maxwell-Stefan diffusivity and the data on unary isotherms that allow us to calculate Qi divided by Pi. Or we could use Monte Carlo simulations to determine the mixture adsorption equilibrium, which allows you to determine the dependence of the component loadings as a function of partial pressures in the bulk gas phase. The component loadings or component permeabilities can be determined also from experimental data on permeation fluxes, but we need a good estimate of the thickness of the microporous membrane layer. In cases where the component permeabilities are difficult to determine from experimental data because of uncertainties in the precise thickness of the membrane layer, we resort to the definition of the component permeance, which is simply the flux divided by the driving force, Ni divided by delta P, and it's the component permeability divided by the membrane thickness. These, the fluxes and delta P's are easily accessible from experimental data, and it is common practice to report membrane permeation performance from experimental data in terms of component permeances. The permeation selectivity is defined as the ratio of the permeability of component 1 to that of component 2, and the permeation selectivity is a product of the adsorption selectivity times the diffusion selectivity, where the adsorption selectivity is given by this expression, and the diffusion selectivity is the ratio of the Maxwell-Stefan diffusivities. Ideally, we would like the adsorption selectivity and diffusion selectivity to complement each other, but this is not always possible. In many cases, depending on the membrane material, the adsorption selectivity and diffusion selectivity do not complement each other. The trick in selecting the appropriate membrane for a given separation task is to choose material where these two parameters, the adsorption selectivity and diffusion selectivity, do indeed complement each other. Start our discussions by considering the separation of mixtures of carbon dioxide and methane. Let's take as an example 50-50 CO2 CH4 mixtures at a temperature of 300 Kelvin and a total pressure of 1 megapascals. Using molecular simulations of mixture adsorption and molecular dynamic simulations of mixture diffusion, we determined the diffusion selectivity for CO2 CH4 mixtures and the adsorption selectivity, and for a wide variety of microporous materials consisting of zeolites, ZIFs, sodium X, sodium Y, mordanite, magnesium MOF 74, zinc MOF 74, copper BTC. We determined the adsorption and diffusion characteristics, and they are plotted here, where the diffusion selectivity is plotted against the adsorption selectivity. We note there appears to be two classes of materials. The materials that are indicated in blue here, ZIF8, Chabazite, ERI, DDR zeolite, ITQ29, LTA zeolite, they all have diffusion selectivities larger than unity. All the materials indicated in black have diffusion selectivities lower than unity, and for all the materials the adsorption selectivity is larger than unity because of the quadruple moment of CO2 and the higher degree of polarizability. CO2 is more strongly adsorbed than CH4 in most known materials. Now, to understand the differences between the blue materials here, these consist of cage type structures separated by very narrow windows less than about 4.1 angstrom in size. For example, ZIP8 has an effective window dimension of 3.3 angstrom. Chabazite has an effective diameter of 3.8 angstrom. DDR zeolite has a window dimension of 3.65 angstrom. A difference in the window aperture of half an angstrom is quite important, as we shall see later. The other structures indicated in black, such as magnesium MOF 74, has significantly larger channel dimensions, typically larger than about 5. For example, MFI zeolite has channel dimensions of 5.5 angstroms. MOF 1 has characteristic dimensions of about 9 to 10 angstroms. MIL 47 is about 8.5 angstrom channel dimension. Faucesite zeolites have typically the window size is 7.2 angstrom. Magnesium MOF 74 consists of hexagonal channels of 11 angstroms. So let us try and understand why in the materials indicated in black here with characteristic dimensions larger than 5 angstrom, the diffusion selectivity is in favor of methane, whereas in the blue structures, the diffusion selectivity is in favor of CO2 and the adsorption selectivity is also in favor of CO2. We first consider mixtures separations using materials that have characteristic dimensions larger than 5 angstrom, and we start with magnesium of 74. From the molecular simulation data on adsorption and diffusion in the wide variety of zeolites and MOFs, we can construct the Robeson plot in which the y-axis contains the permeation selectivity, defined as the ratio of the component permeabilities, as the product of the adsorption selectivity times the diffusion selectivity. The x-axis is the permeability of CO2 in the units of mole, meters per square meter per second per Pascal, and this is determined from a combination of MD simulations of the diffusivity and the configurational bias Monte Carlo simulations of adsorption equilibrium for 50-50 CO2 CH for mixtures at a temperature 300 Kelvin and a total pressure of 1 megapascals. These CBMC simulations yield the ratio of the component loadings at the upstream phase of the membrane divided by the corresponding partial pressures or component fugacities in the bulk gas mixture. The details are available in my publication from 2018. We see here the green line is the upper bound called the Robeson upper bound, and DDR and Chabasite membrane have the highest permeation selectivities, but the permeabilities are significantly lower than for, say, a magnesium MOF 74 membrane or an all silica fungicide membrane. So there is always a trade-off between the permeation selectivity and permeability. What we would like are membrane materials that have a performance that is described by the right corner, top corner of the Robeson plot. The company called NGK Insulators in Japan offer membrane modules which have a monolithic structure, and the inner walls of the tubes are coated with a thin layer, typically about 20 micrometers in size, this layer, and this layer consists of DDR zeolite that allows selective CO2 permeation from a CO2 methane mixture.